Hello, I'm Max Apodaca, and I'll be giving a review of Math 150 in hopefully less than 30 minutes. Let's get started. Do you all remember limits? They were at the very beginning of the school year and are, well, not used a whole lot anymore directly. They are at the basis of everything. So, a limit is defined as a function going to a certain value, and you don't actually have to have the function going to a certain value. Instead, you you only get really, really close to it. So, for instance, here we have a function x ln of x over x, and we're approaching the value 1 from the positive side. And as our values get smaller and smaller and smaller, so do our x values get smaller and smaller and smaller. As our values get closer and closer to 1, so do our y values get smaller and smaller and smaller, all the way until we're almost at 1, but we're not at 1 yet. So if we were to look at this graph, we could evaluate the limits visually. For instance, where the black line intersects the red line, we have a point at the x value -1, we have a limit of -1. If we move from left to right, which is approaching from the negative side, or if we go along the red function to the point of the x value 1, we see that the y value is 1, so our limit would be 1 in that case. If we approach from the other side, which is the positive side, we see that the y value is 4. And if we approach the value infinity, which is something limits can do, we see that we approach approximately the value 0.5. So, certain types of limits you can't just solve by plugging in values, because the function is undefined at that point. For instance, here we have a divide by 0 error, and we cannot do this limit in our previous way. However, we can algebraically manipulate limits, because this is not actually at the point, and we're only going really, really close to the point. So we can make common denominators of the fractions, then combine the two, and then cancel out the x minus 2 and the 2 minus x, leaving a negative sign. And this yields us the limit as x approaches 2 of -2x equals our original limit equal to 2. And here we can now plug in our 2 for our x value. So limits can also be done with infinity. Here we have a limit as x approaches infinity of this function. And, if we plug in infinity, we get infinity over infinity. So we can't just say it's going to be 0 or it's going to be infinity by evaluating whether or not it has a fraction with infinity at the top or at the bottom, because both are infinity. So it's going to have some behavior there. But because it's infinity, we can use highest power rules, which involves removing all terms of a fraction that don't have the highest degree polynomial. Here, our highest degree is 3 on the numerator, and our highest degree on the denominator is 2. So we only are left with x cubed and 32x squared. Now we can cancel out the two x's, and we see that we have x over 32 in the limit going to infinity. Now we're going to have an infinitely large number as the numerator, so we know our limit is going to be equal to infinity. Now sometimes our limits that go to infinity don't equal infinity. For instance, here we have, again, infinity over infinity. But using highest powers, we get x to the 4th over 32x to the 4th. Now we can cancel out our 2x to the 4th, and we get limit as x goes to infinity of 1 over 32. Which equals 1/32. Some limits also don't exist when you're going to infinity. For instance, the limit of sine of x. Sine of x periodically goes up and down between -1 and 1. And there's no value that it ends up approaching as you go to infinity. So the limit does not exist. This also happens, for instance, in our previous example, when if you were to take the limit as x goes to 1 without specifying left or right, then you would have dne, because as you approach the limit point from one side, you get 4, and as you approach it from the other side, you get 1. So continuity and the derivative. So continuity is a way to tell whether a function, if you can draw a function without lifting your pencil. And there's a fancy definition, which is if the limit as x approaches a of f of x equals f of a, then the function is, if that holds true for any value of a, then the function is continuous over everything. If it only holds true for a certain bounds of a, then the function is only continuous within those bounds. So if we were to take a normal slope, which is our rise over run, and instead of using any arbitrary run, we want to use the run n. So here we have the run n for our slope equation. And now we want to make n go to 0, which will give us a slope at a point on the function, or something really, really close to a point. And we write this is the derivative, and we write this as d over dx. So if we want to take the derivative of f of x, we write d over dx of f of x, as shown here. So here I have graphed the normal function, which is in purple, and the derivative, which is in orange. And our slope of our function is positive if our derivative is positive. As you can see, the function goes up, and our slope is negative if our derivative is negative. There's some useful rules that you should know when doing derivatives: the power rule, the product rule, and the chain rule. The power rule says it's pretty self-explanatory. If you take the derivative of ax to the n, you get an x to the negative n. The product rule applies for if you have a product of two functions. For instance, f of x could be sine and g of x could be cosine. And then instead of having to figure out what that is, you can split it up into first taking the derivative of f of x, then multiplying it by g of x, and then taking the derivative of g of x and multiplying it by f of x. F prime of x means the derivative of the f of x function. And if you have a chain rule, which is a function within another function, which could be cosine of sine of x, then you can first take the derivative of the outer function, which is f of x, and keep the inner function, and then just multiply that by the derivative of the inner function. So what can we do with these limits and derivatives? For instance, we have Newton's law of cooling and heating. This can be used to approximate the temperature of an object once you have figured out the K, which is its heating constant. This can also be figured out if, for instance, you know a time that the object has heated or cooled in, and you know the temperatures that it was at. TO is the original object temperature. TS is the temperature of the medium the object is placed in. And T is time, which can be in whatever units you want because it's dependent on the K. And then we can also use derivatives for linear approximations, which are helpful for solving complex equations. For instance, the square root function. It takes a lot of time to do a square root by hand, and it's not fun. So if you know a perfect square, or the square root of a number, and the number you're trying to take the square root of is really, really close, such as 4.01, then you can use the slope of the square root function at x equals 4 to approximate the square root of 4.01. So we do this by first figuring out our equation, which is x to the 1/2 because it's the square root function, then taking the derivative using the power rule in this case, and then using the point slope form, using the derivative of our original function and our x value that's pretty close to approximate this. So now that we know our x value that's pretty close, we can our y in this case here is this is our x value that we know is pretty close, and this is our function output for that x value that's pretty close. So 4 is a nice perfect square, and we can use this to approximate 4.01. So now we can solve this, and we get y is equal to 2.0025, which is pretty close to the actual square root of 4.01. Here's a diagram of what the linear approximation does and how it gets not so accurate as you go further away. So what we're trying to do is keep it within really, really close bounds where the line almost touches the actual function. So you can solve rate equations with derivatives as well. Let's say you have a constant value for c. You know your change in a relative to your change in t, which is time in this case, and you know what your current a is. You can solve for both your b using the Pythagorean theorem and the rate at which b is changing, because you know the rate at which a is changing and you know that c is constant. So you do this by first writing your Pythagorean theorem equation, then implicitly differentiating that equation. So when you implicitly differentiate something, you assume that the variables that you have in the equation are changing relative to each other. So in this case, we're assuming that both are changing relative to time. So then we treat these as functions and just use the chain rule. So we bring down, using the power rule, the outer function to get 2a, and then multiply it by the derivative of the inner function, which is dA over dt. And then we do this for both, and the derivative of a constant is 0. So now we can use the Pythagorean theorem to solve for our b, which is our side length b at when a is 3. And now we can use this b of 4 and substitute it into our original equation up here, and we can substitute in our rate for dA over dt to solve for dB over dt, which we get as negative 11.25, which means b is getting shorter by 11.25 units per second, or per time unit, at when a is 3. So it may be a bit abstract right now what this implicit differentiation is. So if we have ln of a, and we want to take the implicit, and we want to implicitly differentiate this, we first do our normal derivative, which is 1 over a, as if it were with respect to x. But then we need to multiply it with the derivative of a, which is actually a function in this case, which is dA over dx. If we actually were to write this with functions, you see there's a lot of similarities here, where our f prime is dA over dx and our f of x is just a. So how does a derivative determine the shape of a graph? Well, here I have 3 functions. The first one is in green and is a normal function. The second one is in blue and is the derivative of the green function. And then the red function is the derivative of the derivative. So it's the derivative of the blue function. So we can use the blue function, which is the first derivative, which is a derivative of the green function, to tell whether the green function is increasing or decreasing. So if our blue function is above the x-axis, we know our green function is going to be increasing. And if our blue function is below the x-axis, we know our green function is going to be decreasing. And we can see it matches up between the points where the blue function changes. And when the blue function is 0, we have a horizontal tangent, which in this case are local extrema. Extrema is the maximum value. So when on either side of a value, for the y value of a certain point, if you move at all to either side, it's going to be lower. So if we take this value and we move over here, it's a lower y value. And if we take this value again and move over here, we get a lower y value. So the second derivative can tell us concavity. So when the second derivative is below the x-axis, the function is concave down. And when the second derivative is above the x-axis, the function is concave up. When the second derivative crosses the x-axis, that is known as a point of concavity, a point of inflection. So we can see here the function is always curving down, and then it starts curving up once the red function crosses over the x-axis. Some extra cool stuff with derivatives is the mean value theorem, which states that there is some c that satisfies this equation for any b and a, which basically says that if you draw a line between the 2 points of the 2 endpoints of this, which will be b and a, and which will have the x values of b and a, and then so if you draw a y value, a line between the points b f of a, f of b, and a f of a, there will be some point on the function f of x between a and b, so that and this point will be called c, so that f prime of c equals the slope of that line. And Newton's method is a way for approximating the roots of a polynomial, given that you can take the derivative of that polynomial. It's an iterative process that you just repeat ad infinitum. Another cool thing that you can do is optimization problems. So let's say you have 400 feet of fencing and you want to find the largest area that you can enclose with this. So we know that area is length times width, and that perimeter is 2 times the length plus 2 times the width. So we can solve for the length, and we can substitute that into our original equation over here. And now if we take the derivative, we can use the shape of this graph, because it's a parabola, to know that when our tangent line is 0, that's going to be the vertex. And if we set the derivative equal to 0, that will tell us the x value, or in this case w value, where the tangent line is 0. So then we can, so now we have w equals 100, where the tangent line is 0, which will tell us where the maximum is. I made a video on this actual problem, and you can look. It's called the Jolly Rancher problem. It's on my YouTube channel. Antiderivatives. Antiderivatives are a way, are basically doing the exact opposite of what a derivative does. And they're denoted by this integral symbol. There's a few formulas that you have to know in order to do antiderivatives, and they're not, I don't have them listed here because they're listed in most textbooks, and this is supposed to be a review of Math 150 and not a guide on how to do everything. Some useful things to know is that they split up across addition. So integrals or antiderivatives in this case split up across addition. So you can take the antiderivative of f of x plus g of x is the same as taking the antiderivative of f of x and adding that to the antiderivative of g of x. And use substitution is a useful technique that allows you to take antiderivatives of complex equations that you couldn't normally take. There's no way to take the antiderivative of this without doing a bit more manipulation. So what we do is we set u equal to the bottom function. And this works because if we take the derivative of u with respect to x, we get 2x. And the 2 in front of here we can move around, and because it's a constant, it's easy to work with. But we have this x to the 1 first power, which is what we also have in our original function. So if we solve for du over only constants, we get du over 2 equals x dx. And we can substitute the du over 2 and the u equals x squared plus 2 into our original equation to get the integral of 1 over 2u du equals our original f of x, capital F of x. Now it's very easy to take the antiderivative of this. It's just ln of the absolute value of u. Carrying along we can pull out the constant 1/2 in front of the integral sign before we do this. And we add the plus c because no matter what your constant is, it won't change your value of your it won't change your derivative. Now we can substitute back in our u what our u was, and we have just taken the antiderivative of a complex function. So how do we use an antiderivative to find the area under a curve? We use the antiderivative, so between two bounds, a and b, we can find the area under f of x, as shown here in red, by taking the antiderivative, where capital F of x is the antiderivative of f of x, and taking it at point b, at the x value b, and subtracting it from the x value of a. This is based on the fundamental theorem of calculus part 2. So we can do a concrete example with this. Let's say we want to find the area under the curve of the under the cosine function between 0 and pi over 2. Well, our f of x is cosine of x. Our capital F of x is sine of x. So if we now substitute in our b and our a, we get sine of pi over 2 minus sine of 0 equals a. And then we can evaluate our sines, and we get our area equals 1. So now the area between two curves. If we have two curves and we want to find the area between them, we can do this by simply finding the distance between the two curves and then doing a normal integral. Before this, I should mention that an integral is actually creating an infinite amount of... Here, let me go back. So an integral is creating an infinite amount of rectangles and then summing them up. This is called a Riemann sum. So we do this so we can take the area between the two curves by, instead of summing from the x-axis to our function, we want to sum from this other function to our function. So our orange function is x cubed and our purple function is negative x squared plus 3x. So first we want to solve when they intersect. Now I'm only looking at the part of the graph to the right of the origin because they intersect again down here, but I'm ignoring that. So now we can, so our distance between the two functions in the vertical axis is our g of x minus our f of x, where g of x is the purple function and f of x is our orange function. That'll give us the height between here. And then we can use that in our Riemann sum integral, which will go from 0 to from our two intersection points that we found. And we can now evaluate this and we get an approximate area. Now, if you have a triangle or some shape sticking out of your area function, you can also find the volume that's created if you have an infinite amount of these triangles. So in this case, I'll use where the height is twice the base, and then I can solve for the area being b squared. And well, our base in this case is the same height between our two functions. So we can again use what we had earlier, our g of x minus f of x squared this time because we want the area. And then if we plug that into our Riemann sum integral for the same bounds, we can then solve for the volume of this prism-ish thing. So disks, washers, and shells. These are different ways to use your function and spin it around an axis and therefore create volume. So again, you want to use the distance between the two curves, but in this case I'm going to use dy integration, which is, instead of building our rectangles so they stick up out of the x-axis and our dx is our width, we want our dy to be our width, so we go out from the side. This is useful in some cases where you are unable to integrate from one side because, for instance, it's not a function if it's a function of x, but it is a function if it's a function of y. For instance, the x squared graph is a function of x, but it's not a function of y. So again, we want to solve our intersection points, but this time we want to use this formula, which is our f top is our higher function, which in this case, if we're looking at it from the side, so here's our flat line and we're looking at it this way, our top is our orange function and our bottom is our black function. So we want the volume between our two bounds, which are our intersection points, and there's this squared, which is basically using the formula pi r squared to create a disk, which it's then summing an infinite amount of, and then it's subtracting from the inside another disk, which is the area here you see that is covered by the larger disk, but you don't want to be counted in your volume. So we can again do the integral and we get an approximate volume. Now, shells I find easier and basically create a cylinder and then have an infinite amount of these cylinders at different x values. I find them simpler to work with, and the math of actually doing the integral is quite a bit easier, well, in my opinion, and in most cases, if you use a shell. However, sometimes problems will require you to use a disk. So with a shell, you want your radius, which is interesting and a different concept. So if we're doing dx integration in this case, and building our rectangles perpendicular to the x-axis, our radius is going to be how far away from our rotation axis we are. So in this case, our rotating axis is going to be the y-axis. So our radius, if we wanted to use this instead, would just be x. Average values, mean value theorem, and approximate integration. The average value of a function is basically saying if you want to draw a rectangle that has the same area as the function between the two bounds, relative to the x-axis, you could draw it where the y value is this average value for the same width, and you would get the same area. And it's basically taking the average rectangle height. And the mean value theorem says that there will be some value on your original function that is that average rectangle height. And approximate integration is a way to approximate the integral without having to do a Riemann sum. And these are different equations developed in different ways. For instance, here you're creating a trapezoid using the trapezoidal rule, and Simpson's rule, you're creating parabolas to model the tops of the rectangles instead of them being flat across. And the Simpson's rule has an interesting thing where it only works if you have an even number of rectangles that you're creating. Delta x is your step size, which is a fancy way of saying if you take your b minus a and then divide it by how many rectangles you have, that's your delta x. And your x0 is a function, is an equal step between each of the bounds by a proportionate amount to make it so that once you have all of them complete, each one is an equal sized increment. Arc length and surface area are the last two things I'll be covering in this video, and are useful for a lot of things. For instance, if you had a path and you wanted to figure out how long it is, and you had a function to describe the path, you could figure out how long you would have to walk along this red line or curve. You do that using the arc length formula, which from your bound A to your bound B is done by taking the square root of 1 plus the derivative squared of your function, which is basically taking one point and doing a distance formula between a point that's infinitely close, and then taking an infinite amount of those points. And then surface area is the same thing. So your L is your lateral surface area of your figure, and your R is how far away from the axis of rotation you are. So if you want to rotate around the x-axis in this case, you would want to take your arc length, and you would want to, well, in this, it would be easier to do in if it were broken up. And you would have to break up the integral in this case, because no matter how you do it, you hit, if you want to do it with around the x-axis, you hit a function both at the top and the bottom. So you would want to split it up here along where the point is down, and then do two integrals instead. But if you want to do it along the y-axis, rotate this shape along the y-axis and then figure out the surface area of it, you would want to use your radius, which if you want to rotate around x equals 0, you would then use x as your radius, and then your arc length, which is the same as the previous problem. And a little note that the square root sign should actually go over the whole thing here. Now, I hope this helped, and it might not be the best video, but I'm in sort of a time crunch. So thank you for watching, and goodbye.